Hello again. Thanks for joining us. This is Space Nuts. My name is Andrew Dunkley. Hang on. Yeah, that's what it is. Good to have your company on this edition. Coming up, we are going to be looking at a better way of detecting ripples in space. Well, not right now, but maybe soon. Something shiny and new is being developed. And the most distant magnetic field yet discovered. That's very exciting. We'll also be looking at the fastest volcanic region on Mars. Jace has a question about that. Doug wants to know about a carbon star. And Dylan is asking us about the claim that's coming out about dark matter not actually existing at all. We'll tackle that on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9... Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us to solve all these riddles is Professor Fred Watson, an astronomer at large. Hello, Fred.
I'm not sure about that segue because riddle solving is not my strong point, but telling tales about people who do is. So.
Dad jokes aren't your strong point either.
No. Well, that's all right because nobody listens to that TikTok promo that we do. It's more.
Yeah, you're probably right.
Just amuse ourselves, don't we?
Yeah. Anyway, all is well, I assume, Fred?
So far, so good. Thank you. Yes, we're still in one piece. And the northern beaches of Sydney are currently enveloped in smoke as they do hazard reduction burns in the national parks.
That happens, yes. We're getting fire warnings already, although our fire season has technically started, but we had fire danger warnings long before the beginning of the fire season. So things are pretty dry.
Fire season's present in the last all year soon, isn't it?
Yep.
Which is on in the summertime.
Indeed. Now, Fred, let's get down to it. And our first story is looking for ripples in space. Now, we're probably talking gravitational waves here, I assume. And like we have got gravitational wave detectors, but this one's a brand new, shiny one with bells on, by the sound of it.
Maybe it'll have bells, yeah. Something that goes ding when the laser switch is on. Look, it's one of the great science stories of our time, Andrew, is the fact that we can now detect these ripples in space. I don't know why I nearly called you Richard then. I've no idea why. Anyway, never mind, Richard. Used to be Dave. But the fact that we can detect ripples in space is, an extraordinary achievement. It was predicted. They were predicted by Einstein a century ago, but it wasn't until 2015 that the LIGO, I think it was called Advanced LIGO, its technical term, detector in the US actually detected the first shaking of space-time due to gravitational disturbances in the distant universe. Just bearing in mind what LIGO stands for, it's an acronym. It stands for Laser Interferometric Gravitational Wave Observatory. And that tells you that it uses laser beams, 4 kilometers long in the case of LIGO, two at right angles to one another, which means that as space shakes, you will sense it in any direction. And there are two of these detectors at opposite corners of the United States, so that you can get some idea of where the shaking's coming from by the time difference between one picking up a signal and the other picking up an identical signal. And that's because the gravitational waves travel at the speed of light. And so, you can get something like a few milliseconds difference between the arrival of the two shakings at LIGO, and you've suddenly found at least some idea of where it's coming from. In order to refine that directional sensitivity, what you need is more gravitational wave detectors. And so over the last few years, LIGO has been joined principally by two more, Virgo in Italy and Kagra in Japan, which all work together with LIGO, with the two LIGO detectors, and it gives you much improved sensitivity to the direction in which gravitational waves come from. However, like everything in astronomy, you're limited by the instruments you've got in terms of their sensitivity. So we always want to look at more distant things or pick up things that are fainter or weaker. I mean, hobby astronomers get this illness as well. We call it aperture fever. You always want a bigger aperture telescope because the thing that you really want to look at is just too faint for you to see with the one you've got. And that's a similar situation in the world of gravitational waves. And so there has been thought given, including here in Australia, actually, there's quite an enthusiasm for setting up a gravitational wave detector in Australia. The one thing that's likely to knock that on the head is the price tag, because they're not cheap. And that's because bouncing laser beams along 4-kilometre long tunnels, as they do with LIGO, is a very difficult thing to achieve. The mirrors at each end have to be super precise and take into account quantum physics and all sorts of things in order to work properly. So the LIGO detector is state of the art. But what we're talking about today is what might come next. Yes. And that is bigger and better. I did say shinier, and maybe it is shinier because it'll have to have a bigger laser. Because where LIGO bounces its laser beams backwards and forwards along 4-kilometre tunnels, this one, which is being called Cosmic Explorer, will do it along 40-kilometre long.
Whoa, really?
Yeah, that's right. And what that does, assuming that it works and it can be built, what that will do is improve the sensitivity. So it means that the colliding neutron stars, black hole neutron star collisions, black hole collisions, which are the stock in trade of the LIGO detectors, they will all come in loud and clear, but from more distant sources. So you'll improve the sensitivity. And in fact, there's expected to be something like a 100-fold improvement in sensitivity by going to 10 times longer laser beams. Yeah. But so this story actually is, I think, come from the MIT news website, MIT being the Massachusetts Institute of Technology, which is actually leading this proposal. And the reason why they've hit the headlines is that they've received $9 million of funding from the National Science Foundation over the next 3 years to get the design phase underway, because designing a gravitational wave observatory is not something you can do with a pencil and a ruler and say you need a straight line 40 kilometers long. Oh, that's fine. A mirror at each end, no problem. It's actually a lot more complicated. So the kind of problems, and this is the intriguing part of this story, I think this is why I thought it would be a really good one to do, Andrew, is that you need to take into account such things as the curvature of the Earth.
I was just thinking that. I was going to say, how are they going to solve that problem? Because a laser will just go dead straight, but there's over 40 kilometres, whatever it is.
That's right.
There's curvature. Do you just keep building struts to hold it up?
Well, I guess you probably have to bury the middle bit.
Yeah, maybe
in the ground. But what they're suggesting, the sort of experts who are interviewed in this MIT press release, is you need to specially choose a site that's going to minimise that effect, and so. What you would like is a place that's slightly bowl-shaped, and that means that your straight line underneath it, you don't have to dig as deep for the middle parts of it if you've got a bowl-shaped region. It needs to be pretty flat, but slightly dished would help, because that curvature that we've just been talking about would be compensated for kind of automatically. And then there's, you've got to find somewhere that's not in a mountainous region. And then you have to find somewhere where you can actually get people in and out. So it can't be totally inhospitable, although you don't want to be too near centres of population, because that gives rise to seismic effects. You've got ground shaking, which, of course, can overwhelm the faint signals coming from space itself shaking.
Yeah.
So yes, they do see it as a possible replacement for LIGO, which would kind of make LIGO redundancy because of its improved sensitivity. And they're talking about the mid-2030s, which actually seems a little bit optimistic to me, given that LIGO started, I think, back in the 60s, and it was only in 2015 that they actually made their first detection of gravitational waves. But it's a great story and something to watch out for. Maybe in a decade or so, when you and I are with our Zimmer frames and croaking at each other with terrible dad jokes, we might be able to talk about its opening ceremony and things of that sort.
Yeah. So I assume they haven't chosen a location yet.
That's right. The location is yet to be decided. What's kind of exciting, though, is what they're talking about is every year, rather than getting 10 or 20 neutron star mergers, as we do with LIGO, you get 1 million because of the improved sensitivity and hundreds of thousands of black hole collisions that they're talking about just by improving the sensitivity of the detectors. And that's all about the length of it. I guess one other thing to put into perspective here, though, is a project called LISA, which you and I have discussed briefly. LISA is, if I remember rightly, the Laser Interferometer Space Antenna. I think that's what the acronym sounds.
Yeah.
And it's an ESA project, European Space Agency, to put mirrors which are more than 100 kilometers apart in space. And so you've got a beam length of more than 100 kilometers. And they had a proof of concept mission a few years ago, which I think you and I reported on for Space Nuts, which was incredibly successful. They showed that the technology of how you keep these things in space, but know their separation to within a tenth of the diameter of a proton or whatever it needs to be, that it can be done, that the technology exists to actually do this. Now, the funding doesn't exist to do it yet, but LISA is certainly very much on Europe's horizons. It would be really interesting to compare what the Cosmic Explorer project, what we're talking about from MIT, what that would cost in relation to a possible LISA pair of spacecraft, or it would be probably 3 spacecraft at the 3 corners of a triangle with lasers going between them. Interesting technology, Andrew, with lots of possibilities.
Yes, indeed. And remind us again why this is important. Why do we need to do this?
It's just a new window on the universe that was one that we always knew might be possible, but had never happened until 2015. So the traditional astronomy uses electromagnetic waves, whether they're light waves or radio waves or gamma rays and X-rays from space, because they don't penetrate the atmosphere. That's electromagnetic astronomy. Then we've got particle physics astronomy, where we're actually looking at subatomic particles that come down to us from space. And the other sort of arm in our bow these days is the idea that we can actually sense the shaking of space itself, which is caused by gravitational effects. And that has potential really way beyond what we can imagine, because eventually all these things will basically tie in together. They do to some extent now. I think I'm right in saying there's only one type of merger, and I think it might be neutron black hole mergers, that actually gives you an electromagnetic flash rather than just a rippling of space. And that's actually been observed. It's how we know precisely that gravitational waves travel at the speed of light, because the flash arrives at the same time, effectively. So there's all that. But gravitational wave astronomy has some other intriguing prospects. So the sort of frequencies of the gravitational waves that are being detected now, and I think this is going to be true as well as of the Cosmic Explorer, if and when it's built, these are frequencies that are in the audio region of the acoustic spectrum, even though it's not acoustics, it's space itself that's shaking. Whereas if you go to different frequencies, you can sense different sorts of events. And the Big Bang itself, or at least the epoch of inflation, which immediately followed the Big Bang, would have produced a gravitational wave signal. But that, if, as I understand it, the frequency of that signal is so low that you never see any change. It's not gravity bouncing up and down. It's something that's virtually constant because the frequency is measured, I think, in millions of years rather than, or one per million years rather than, 50 cycles per second, which you get in the audio frequency.
So bottom line is we can learn a lot.
We can learn a lot. That's right. Sorry to answer the question. You just asked me. I'm going to put my mic on mute because I'm going to have to cough.
Okay. Yeah. Coughing is legal. Yes. As long as you don't give someone a disease.
No, it's on the internet anyway. It's not legal while you've got the microphone.
No, of course not. All right. Okay, and if you do want to read that story, it's on the spacedaily.com website. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Come unwrap some holiday magic this season in Denver, where the lights are brighter and the shopping is grander, where the season feels a whole lot more wonderful. Discover great hotels and more things to do at milehighholidays.com.
Experiences are what people love the most about travel. That's why they love Viator. They have over 300,000 bookable experiences and something for everyone. Plus, their travel experiences have millions of real traveler reviews, so you have the information you need to book the best activities for your trip. Download the Viator app now and use code Viator10 for 10% off your first booking in the app. One app, over 300,000 travel experiences you'll remember. Do more with Viator.
3, 2, 1.
Space Nuts.
And it's good to have you along. Let's go on to our next topic, Fred, a distant magnetic field discovery. This is the furthest one ever seen as far as we know. Probably. Well, we do know it is the furthest one away that's ever been picked up. Is that right?
That's right. Yes, it is. It's really extraordinary work. We have to choose our words carefully here, Andrew, because I believe that one of the authors of this work who made this discovery is going to be listening to this episode.
Oh, okay.
So he's probably going to keep us honest. His name is Rob Iverson. He works for the European Southern Observatory, and he's a millimetre wave astronomer with a similar sort of history to mine in that he worked in Edinburgh for a long time, but he comes from the north of England, so he speaks a lot like I do. So that's the backstory. And what I'm going to do now is mangle it completely in order to put it into the way I understand it. So the telescope that features in this story is, of course, ALMA, the Atacama Large Millimetre Submillimetre Array, operated by a consortium which does include the European Southern Observatory. It's in the Atacama Desert. I've visited it. I've visited their sort of low-level station. I tried to get up to the antennas at one stage by going in the back door, but the road takes you to 5,000 metres above sea level, and breathing became quite a problem, so I never got there.
Especially given how tall you are.
Well, that's right. Yeah, that adds another, half metre onto normally would be. It's the first time I've really felt ill from altitude, and I do remember sitting in the car. I wasn't driving, actually, and sitting in the car and thinking, I don't feel very well here. Quite glad to get down, a couple of thousand metres lower down. The nearest town is San Pedro de Atacama. It's a delightful little town of much quaintness, and I think that's where a lot of the ALMA technical staff and operators live in northern Chile. Very interesting part of the world. Not very far from where the very large telescope is at Cerro Paranal.
And the BLT telescope, of course.
Did you say the BLT?
Yes.
Bacon, lettuce and tomato, is that
That's
right?
the one.
Yeah, that's it, yeah. Yes, that's right, which is at Cerro Amazones, if you mean the extremely large telescope. So what's the story? Well, ALMA is really sensitive to millimetre and submillimetre waves. In other words, these are basically very, very short wavelength radio waves. They almost stray into the infrared region of the spectrum, but not quite. But there's that sort of grey area maybe between what's called far infrared and the millimetre submillimetre region. the spectrum. And the problem with trying to observe at those wavelengths is that you are very susceptible to any water vapor in the atmosphere. Water vapor in the atmosphere is a killer. That's why ALMA is sitting at nearly 5,000 meters in one of the driest parts of the whole planet in northern Chile. And that's what gives it its exquisite sensitivity, the fact that it is free from all the damaging effects that you would get if you tried to put a millimeter wave telescope, say, in Sydney or somewhere like that. It's very radio quiet as well, but that's probably less important than the water vapor. So a team of astronomers led by James Geach, who's from the University of, that's how his name's pronounced, University of Hertfordshire in the UK, along with colleagues including Rob Iverson, who I've just mentioned, our friend from ESO. So what they've detected is a galaxy which has a strong magnetic field, but this galaxy is not, like the Andromeda Galaxy, 2.5 million light years away on our doorstep. This galaxy is 11 billion light years away in the frame of reference that we see now. I always say it's better expressed by saying it's got a look-back time of 11 billion years because the universe has expanded in that 11 billion years, so its distance is certainly more than 11 billion years as the crow flies, but we have a look-back time of 11 billion years. And so the universe itself was, only about 2.8 billion years old with our best estimate of the age of the universe. And here's a galaxy with a magnetic field that is, I think, as far as I understand the story, comparable with the magnetic fields of galaxies that we observe today. It's very weak compared with the magnetic field that you and I are sitting in now, the planet's magnetic field. It's about 1,000 times weaker than that. But unlike the Earth's magnetic field, this one extends over more than 16,000 light years. So it is it's a galaxy scale magnetic field, and that's really a curious thing to find a large and well-defined magnetic field so early in the universe. In fact, I'll quote Rob Iverson himself. He's quoted in this press release. He says the discovery opens up a new window into the inner workings of galaxies because the magnetic fields are linked to the material that's forming new stars. So you're talking about a time when stars were rapidly being formed in the early universe. And there's clearly a really interesting interaction between these large-scale magnetic fields and the way the stars themselves are formed and evolve. And I might just add that sort of magnetism on this scale, the magnetism of the universe as a whole, is a bit of a mystery. How did it form? How did things get magnetized?
Boy Scouts making compasses. That's how. That's what happened.
Well, probably yes. I remember getting bits of soft iron and banging them with a hammer so that they picked up the Earth's magnetic field. But of course, there's nothing. Well, there aren't any hammers. There could be Boy Scouts in the early universe, but you never know. The whole origin of magnetic fields is a question, and it's actually one of the fundamental questions that the Square Kilometre Array is being funded to ask. How do magnetic fields start? How do they evolve? What's the story about the magnetism in the early universe? Well, these ALMA observations throw a bit of light on that already. I'm going to shut up and let you ask a question, which I hope will be, how did they detect this?
Well, yeah, obviously. How did they detect it? And I'm gathering from what you've been saying and what's been announced that it's the enormity of this that is quite exciting and staggering.
It's big and it's galaxy-sized. So the question of how you detect this is coming from something that the Atacama Large Millimeter Array is peculiarly well adapted to detect, and that is the polarization of radio waves. Polarization is such an extraordinarily powerful tool in the world of astronomy, but it's something we seldom talk about because we talk about spectroscopy, the breaking up of light into its component rainbow colours, whether that's radio waves or light waves or whatever. And that's, of course, perhaps the most important tool of astronomers. But polar emitters, the devices that detect polarization, are equally important, particularly when you get to these longer wavelengths. Like infrared astronomers and millimeter wave astronomers are very obsessed with polarization. Why is that? Well, because certainly in the millimeter and submillimeter region of the spectrum, you're detecting radiation that's coming from dust grains. So the galaxy itself is very dusty. Our galaxy is dusty. It's why we can't see directly to the galactic center, which passes above us, on winter nights here in Australia, because there's dust clouds in front of it. So galaxies are all like that, very dusty, but the grains of dust tend to line up with magnetic fields. So if you've got a magnetic field and you put dust in it, the dust will tend to sort of line up with the magnetic field.
Yeah, we used to do that experiment in science classes.
That's the one. Yeah, with
iron filings.
Iron filings, that's the one.
Yeah.
It's the same sort of thing. But that means that this is the trick, that the radiation that they then emit is actually polarized. So you can detect that polarization. And when you see swaths of radiation coming from large areas of, say, a galaxy, all of which is polarized in the same direction, it's telling you that there's a very large magnetic field there.
Mm. So that's what's happened here.
That's exactly what's happened here. That's right. So that's how ALMA can detect the fact that there is magnetism there. It's amazing stuff. We have colleagues here in Australia who sense the polarization of light, which is the sort of thing we use with polarizing sunglasses, but very much more refined.
Yeah.
And it turns out that the polarized light could tell you a lot about, for example, the atmospheres of exoplanets, planets around other stars. And one of my colleagues, Jeremy Bailey, one of his missions is to detect the polarization of rainbows in the atmospheres of other stars, which is a thing to do.
Yeah.
Yeah, he's built a polar emitter that's probably sensitive enough to do that as well. But that's a different story from what we're talking about now. But I just threw that in so you get an illustration of just how important polarization is as an astrophysical tool.
Yeah, you know they recently discovered the weight of a rainbow, didn't they? It's pretty light.
I thought you'd save that for the TikTok announcement.
But you talked about rainbows. I couldn't let it go.
It's a good one. I like that.
That's
light.
not bad, is it?
Yeah, not bad.
Oh dear. And these strong magnetic fields also explain Rob Iverson's hair. Sorry, Rob, I couldn't help myself.
Well, Rob Iverson's got the same hairstyle as me.
Yeah, I was going to say, I'll bet he's got the same. Well, that could be it too.
Yeah, it could be a trick. I'm sure I'm highly polarized, Andrew.
Yeah, that might be a thing.
Yes.
Yeah. No, it's great news, and I'm still staggered by the fact that we can make discoveries that are so very far away and learn in detail what's going on. It blows my mind.
Mine too. And just wait till we get the Square Kilometre Array Observatory and maybe the Cosmic Explorer gravitational wave detector.
Yeah.
We'll be blown even more, I'm sure.
Has this galaxy got a name, by the way?
Yes, it's. I've got to see if I can remember that. I think it is 9I09.
Okay. Yeah, another well-named astronomical
might be a trick to that
discovery. Yeah, maybe.
I'll have to get Rob to explain why it's called 9I09.
I'm just looking at the report now. Apparently, this was also discovered in the course of a citizen science project through the BBC.
Originally,
Isn't that amazing?
Yes, not only the BBC, it was their what was it called I can't remember the name of the
Stargazing Live.
Stargazing Live, that's right. Which came to Australia a couple of years. So
you were involved in that.
I was. Yeah, great fun.
You were there
with young Brian Cox and other famous people. It was good fun. Stargazing live. So yes, we did actually citizen science projects when we were on air in Australia. One of them was about exoplanets, discovering exoplanets, and that was successful too. Can't remember what the other one was. Too long.
Fair enough. All right. Fascinating news, and you can read all about it at the eso.org website. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Experiences are what people love the most about travel. That's why they love Viator. They have over 300,000 bookable experiences and something for everyone. Plus, their travel experiences have millions of real traveler reviews, so you have the information you need to book the best activities for your trip. Download the Viator app now and use code Viator10 for 10% off your first booking in the app. One app, over 300,000 travel experiences you'll remember. Do more with Viator.
Roger, you're allowed to stay here also.
Space Nuts.
Now, Fred, we come to the end of the show. Well, no, it's not quite, because people send us in questions and we try to put them somewhere where we can't find them, but they always turn up. And so we've got a few today to deal with. This first one comes from Jace.
Hello, Fred and Andrew. This is Jace from Adelaide. I've got a question that's been on my mind for years. And the question is the Tharsis volcanic region on Mars the result of the Hellas impact? So the Hellas impact is the huge crater on the opposite side of the volcanic region of Mars. So if shockwaves travelled through the core or around the surface of the planet, would that result in volcanism on the other side? Maybe not directly opposite, maybe it's due to the angle of the impact or the various density of the rock. So imagine we've got volcanic activity in the Tharsis region continuing for many millions of years after the Tharsis impact. So that increases the atmosphere and the temperature and the pressure, and that allows the surface oceans to appear. So if there's an extended period of time between the Hellas impact and the end of the Tharsis region, could that volcanism have increased the pressure and allowed water to form on Mars? Thanks.
Wow. He's put a lot of thought into that. I love a question that comes with a theory. Thanks, Jace. So explain the Tharsis region to us first, Fred.
Yeah, so it's an elevated plateau on Mars, which has a number of now extinct volcanoes on it, or near it as well, including the tallest mountain in the solar system, tallest volcano in the solar system, Olympus Mons. That's right next to the Tharsis.
Is it called the Tharsis Bulge? Have I heard that somewhere?
You could do, yeah. It's So often the Tharsis Plateau or just the Tharsis region could be a bulge, because that's kind of what it looks like.
Yeah. And
Jace is right in that it's kind of on the opposite side of the planet from the Hellas impact basin, which is, I think, if I am remembering correctly, is the fourth largest impact structure in the whole solar system. So it's big. I suspect the Aitken South Pole Basin on the Moon is bigger, but it's really quite extraordinary. This thing's a dent in the surface with something like 7 kilometers of depth compared with its surroundings, and that's why on topographical maps of Mars it appears as a big blue blob, because blue is usually the color code given to low-lying regions. It's just a very, very large area of low-lying land, about 2,500 kilometers in diameter. So it is tempting. So now that impact basin is thought to have been formed pretty well at the same time as the South Pole Aitken Basin on the Moon during this period we usually call the late heavy bombardment, which is very early in the history of the solar system, 4.1 to 3.8 billion years ago, thereabouts. And it would have been a very big asteroid that would have hit the surface to form that enormous structure. Now, the origins of the Tharsis region, I don't think they line up in terms of their age, because I think
that's always a telling factor, isn't it?
I think they're younger than that. Although, let me see if I can find an age for some of the Tharsis volcanoes, because that the thinking as to why that Tharsis region exists is slightly different in terms of its origin, and that is that we know that Mars does not have tectonic plates, so the crust of Mars is like the skin of an orange. It's continuous. It doesn't have breaks in it. And so if you've got a hot spot underneath the surface, a magma hot spot, and then that breaks through to form a volcanic region, exactly like the islands of Hawaii, because Mars doesn't have tectonic activity, that hot spot always stays under the same bit of the crust.
Yeah.
And because the crust's not moving as it is in the Hawaiian situation, which is why you've got this string of islands. And so it just keeps on pumping out stuff in one place, and you get these extraordinarily high mountains like Olympus Mons, 23 kilometers, I think, is its height. So that's the origin of the Tharsis region, as I understand it.
Now, I've just done a bit of a quick check,
I hoped you would.
And what I'm being told is the Tharsis region is around 3.7 billion years old.
Yeah.
And the Hellas impact region is between 3.8 and 4.1 billion years ago.
Yeah. So that's right. I mean, it's tempting to imagine that Hellas impact might very well have shaken things up on the opposite side of the planet, because that's how seismic waves behave. They get focused by the core and come up on the other side. So, it may be that the original fractures that gave rise to the volcanic activity in the Tharsis region might well have been the result of the Hellas impact. But the fact that it's an elevated plateau is just because for such a long period of time, stuff has been pumped out onto the surface because of the hotspot underneath it. Now, maybe the hotspot itself had its origins in the Hellas impact. There's a great scenario that Jace is saying. In terms of the details of a warm and wet climate, things of that sort, I'm not sure to what extent that is likely to be the case, but it does seem, as I said, just seem tempting to link these two things together. What you need is a Mars expert. That's what you are, isn't it, Andrew?
You do. It's red. I see. That's as much as I know. I like his theory, and you can't absolutely dismiss it, because something huge smashing into Mars, it's got to have a ripple effect.
Well, it's certainly got. You expect it to have planet-wide consequences, and
so they may be linked. Their time frames aren't that far apart in the history of the planet, so it's it could have happened that way, Jace.
It's about. Sorry, I was just going to say it is about the time when we know Mars was warm and wet as well.
Okay,
same sort of period. So yes,
you might be onto something, Jace. Write a paper, get yourself published, get it peer reviewed, and then go to the pub and get a beer reviewed, and see, someone will believe you.
Passing the pub test.
Yes, that's always important. Thanks, Jace. Next, we've got Doug, who's got a really interesting question for us as well.
Hello, Dr. Watson and Mr. Dunkley. This is Doug Stoneback from Boise, Idaho. And I was just wondering, we were looking at a carbon star called La Superba. It's a red giant. And just wondering if, or one, this turns into a planetary nebula, would it show the same color because of its richness in carbon in the atmosphere? Are there any planetary nebulae that came from carbon stars? And thirdly, in regards to the blue snowball, the blinking planetary, and the Cat's Eye Nebula, of course, they're all a bluish and turquoise type of color. Is that due to their atmospheric makeup? Could it possibly be methane, as in Neptune and Uranus? I'd love to know the answers to these questions so I can pass this along to the public. Thank you. And have a great day and keep up the fabulous work.
Good on you, Doug. Strange surname, Stoneback. Anyway, sorry, that one went straight over your head. You'll know what I meant. Carbon star. I suppose we should explain what a carbon star is first.
That's right. So they're stars that are rich in carbon, as you might expect. I think they're defined as being stars whose atmosphere has more carbon than oxygen. If you get carbon and oxygen together in the upper layers of a star where temperatures are a little bit cooler, you can get the formation of carbon monoxide. And essentially, the carbon itself becomes almost like a soot around the star. A sooty atmosphere, it's sometimes described as. They often have a characteristic red appearance because of that sootiness, I guess. It's a facility or a feature of stars that they're highly evolved, which means that they're at a late stage in their evolution. And as Doug mentions, they probably not too far down the track, they will turn into planetary nebulae, where they start basically emitting clouds of material from their outer layers that form these rather symmetrical nebulae, called planetary nebulae by William Herschel, who thought they looked like planets, even though he knew they were nothing to do with planets. That's because they're disc-like, they look round. And that's the stuff that's been emitted. So, so the carbon stars themselves, great interest. I'm not an expert on carbon stars. I used to work with people who were. But once again, and we've talked about this already in this episode, one of the critical aspects of carbon stars is the dust that surrounds them. So they've got a sort of, because they're relatively cool stars, that means dust grains can form. And so you can get dusty planetary nebulae from them. And the dust gives rise to different colours. So I think he's kind of on the right lines there. I'm not picking up on the details that Doug was asking about, but different colours from the way dust grains, for example, reflect light. Dust tends to be reflected with a blue colour. We call them reflection nebulae, and it's because of the fact that dust scatters light in the same way as the Earth's atmosphere does. The Earth's atmosphere is blue, and reflection nebulae are themselves often blue because of that. So it's one that's worth checking up on. I don't think Doug would have to work too hard to get the specific answers to the individual stars that he was talking about there, and individual planetary nebulae. But there may well be a connection with carbon stars with some of those individual planetary nebulae.
Yeah, I think he was talking about whether or not some of those nebulae were methane-based.
Yeah, that's right. And, these are, once again, that's a molecule, which means you're talking about cool, relatively cool regions of space. Maybe so. Whether you can draw a parallel with Neptune, and Neptune in particular, which is definitely blue because of largely because of the way methane observes light. I don't know whether you can make that comparison with planetary nebulae. I suspect not, because I think the temperatures are higher in the planetary nebulae.
Yeah, sounds more like a dust kind of scenario. Just bouncing the light around.
That's it.
Okay. Thank you, Doug. Lovely to hear from you. And our final question this week comes from Dylan.
Hey, Andrew and Fred. Dylan from Fremantle in West Australia here. I'd like to ask you a couple of questions regarding an article I read around a month ago related to dark matter, more specifically an article that appears to disprove the existence of dark matter in favour of a modification of the laws of gravity. The article said that physicists had observed tens of thousands of pairs of wide binary stars up to a distance of 650 light years away using data from the Gaia mission, and it detected a deviation from gravity as predicted by Newton and Einstein. The deviation was, to a layman like me, an absolutely crazy figure. From memory, I think it was at speeds of 0.1 nanometers per second squared, acceleration was higher by around 30 or 40% than predicted. The article then went on to say that all of the observations had been at 5 sigma significance. So my two questions relating to this are, first, how on earth are we even able to detect such an incredibly low acceleration rate at such a mind-bogglingly vast distance as 650 light years? And second, given the implications for all of cosmology, not to mention that I would think the discoverer would be a shoo-in for a Nobel Prize, why hasn't this story blown up worldwide in mainstream media? Do these things sometimes take a while to filter through, or did the research have a fatal flaw? To me, this was one of those I will always remember where I was when I heard this moments. Dark matter, mystery, solved, incredible. So I very much hope that this is true, and I'd love to hear your thoughts on this. Thank you very much for your podcast. I love it. Take care. Bye-bye.
Thank you, Dylan. And I love Fremantle. Visited there once, and it's just such a pretty place, so much to do and see, and a really enjoyable part of the world. Why no media attention? Probably because they just didn't understand it. No one knew what to write.
No, I think
that'd be my answer.
Yeah, I think it's more more academic than that. That might be the right word. In that, I think these results are still being churned over. And peer review is one thing, but to be accepted by the community of astronomers is another. One of the reasons why the idea of modified Newtonian gravity hasn't taken off already is that it doesn't work in all situations. It might help you get rid of dark matter as something that holds galaxies together. But then you feed it into the bigger picture, and you find that the universe can't exist the way it does if we've got rid of dark matter.
Yeah.
So it's a many faceted thing, and if we do eventually ditch dark matter in favour of modified Newtonian gravity, Mordecai Milgram's theory of the 1980s, which is what is still being talked about, then it will be something that takes time. It will be a shift in paradigm. It won't be headlines. It'll be, there might be one headline when some critically or very a key astrophysicist throws out dark matter formally, but at the moment the pervading view of the universe is that dark matter is real, that there is still some subatomic particle that we have not yet identified that constitutes that. Just because that fits it fits all the observational data to the best of our knowledge. Now, every so often something comes along, like the things Dylan's mentioned. I think we talked about this paper actually about the binary stars. Maybe we didn't.
Maybe that rings a bell. Yeah, it does ring a bell.
And these are, as you said, it's tiny accelerations measured in nanometers per second squared. And you can do that because you're talking about things that take place over length of time, reasonably long periods of time. You're talking about distances that are very large. And by that I mean not the distance to these wide binary stars. So wide binaries are pairs of stars that are in orbit around one another, but at very high separations. And I think the general opinion is that there is something fishy about those, that there is something that doesn't fit the bill properly. And it may well be that there is something wrong with our understanding of Newtonian dynamics, but it can't be the whole picture, because that doesn't account for some of the things that dark matter does account for. When we look, for example, at the early universe, the origin of structure in the universe, you need dark matter for all those things to happen.
Maybe there's some parts of the universe where there isn't dark matter, doesn't matter.
Yes. None of it matters really, does it?
I don't know.
So, but look, I'm really happy that Dylan's picked up on this, because I think it is a story that's not going to go away. It will It'll be churned over by the astronomical community. There might be a conference about it at some point if it gets to that level where astronomers are sufficiently intrigued by it that they think it has legs more than we originally thought. So, yes, watch this space.
Well, it may be cracking the mystery of dark matter. Might be that there isn't dark matter after all, and might be something else. But they've got to get the mathematics to add up.
Yeah, everything's got to add up across all scales. It's not good just looking at wide binary stars. You've got to be able to deal with galaxies. You've got to be able to deal with clusters of galaxies. You've got to be able to deal with the cosmic web. And not only that, you've got to be able to deal with gravitational lensing, which is one of the key reasons why we think dark matter is real. When we look at the gravitational properties of distant clusters of galaxies, the effect they have on the images of background galaxies speaks of much more mass in them than what we actually can see, and that's dark matter.
Fascinating stuff. Thanks, Dylan. Lovely, great questions today. Really deep thought stuff. Yeah.
Challenging.
Indeed. Thanks also to Doug and Jace for sending in questions. Don't forget you can send us questions too via our website, spacenutspodcast.com and spacenuts.io. And just hit on the AMA link to send us a voice or text question, or the little tab on the right-hand side, that mauvey, purpley, violet one, where you can send us voice question or a voice message. You don't have to send a question. You can just send in a message. Some people just do that. That's fine. Just don't forget to tell us who you are and where you're from. We do like to know. We're all wrapped up for another day. Fred, thank you very much.
Great pleasure, Andrew. I look forward to seeing you next time.
Indeed. See you soon. Fred Watson, astronomer at large, part of the team here at Space Nuts. And I'd normally say thanks to Hugh in the studio, but we didn't tell him we were recording today. And from me, Andrew Dunkley, great to have your company. Looking forward to catching up again on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.